Welcome to video number 2, where I'm going to show you how to estimate the benchmark VAR model that we're going to use to compare with the local projection method.
If you're passionate about understanding data and the economy, you are in the right place. Before we start with today's tutorial, I would like to invite you to hit that subscribe button. It's free and it really helps the channel grow and reach more people like you.
So in the paper, Jordà uses the empirical application of Evans and Marshall 1998 paper as a benchmark to compare vector autoregressive based and local projection based impulse responses. Evans and Marshall's, they study how monetary policy shocks affect the yield curve using a 6-variable VAR with the Cristiano, Eichenbaum, and Evans 1996 recursive identification. Using monthly data, the authors compute a vector autoregressive model with 12 lags. The variables that they use in the model are the log of non-farm payroll employment, the PCE deflator, smooth change in commodity prices, federal funds rate, non-borrow reserves over total reserves, and the log growth rate of M2. The shock identification is done using Koleski ordering with the federal funds in the fourth place. We are going to have the log of non-farm payroll employment, PCE deflator, and the prices of commodities first, which they are not going to respond contemporaneously to the monetary policy shock. Please guys, remember that I have already explained vector autoregressives, so if you need to refresh the topic, please make sure to watch the tutorials. I have put in the description of this video all the links for you to be able to go through vector autoregressive models. By the end of this tutorial, we are going to be able to compute impulse response functions like the following. I'm in Stata. I have a do file editor open. Step number 1 is to import the dataset. I have included the dataset in the description of the video. You can download this dataset. In this particular case, I already put it into a Stata data file. So this is the way I named this data file and how you're going to be importing this. Next, we're going to t-set our time variable. In step number 2, we're going to estimate the VAR model. I'm not going to go through all the details of the model because we are replicating a paper. I'm using the VAR command to estimate the VAR model. We are now typing all the variables that we have in our model. Let me include now the money. Lags, we're going to be using 12 lags as the authors have used. In step number 3, we're going to compute the impulse response functions. First, I'm going to set a file where we're going to store all the different models that we're going to be estimating. In this particular case, I have called this VAR12 underscore IRFs. You can name this the way you want. There's no constraints here, as you know. You can just set the name to whatever you would like. I'm going to create, in this particular case, a model that I'm calling VAR12. We're going to be including 24-step horizons in our model. And finally, I'm going to compute the graph of the impulse response functions using an orthogonal identification. I'm going to use here, our impulse is the federal fund rate, and the response are going to be all the rest of the variables in the model. Important, as I mentioned, if you are not familiar or you don't remember the syntax, please make sure to go through the tutorial where I already covered this with a lot of detail. We're going to be running or executing this do file now, and we're going to be analyzing the results. All right, here we have the output of the vector autoregressive model. We have all the variables with all the coefficient estimates of the model. Remember, each of these variables includes 12 lags, so this is what you are seeing here. And next, we're going to look at the impulse response functions. Here we get the graph. I'm going to maximize the screen. And you can see that by default, Stata is going to produce the impulse response functions, but something that you're going to notice is that the scale is not going to be very helpful for these particular responses. But unfortunately, with Stata, we cannot modify the axis here, how the scale of the responses. So unfortunately, using the default structure of impulse response functions by Stata is not going to work the best. So I'm going to teach you now how we're going to manually create the impulse response functions. So that way we can have images that look exactly like these ones that are appearing right now in the screen. To generate those professional impulse response function graphs, I'm going to show you how you can extract the IRFs from this file, from the IRF file. So I'm going to be using then the file that we had called VAR12 IRFs. I'm going to put here clear. And from this file, what I want to keep are the impulse response functions. Let me IRF name. Here we go. That's the right syntax. And this is the model that we have called VAR12. That's exactly what we have created here. What I want to keep is the impulses. In this particular case, I don't want to keep all the impulses. The only one we care about is the federal rate shock, okay? And something that I would like is to keep just some elements of this table of data. I don't want to keep everything. All I want to keep is the responses, the steps, the orthogonal impulse response functions, and then the standard deviations of the IRFs. So this is all that we're going to be typing here. And now we need to generate one thing. We need to generate the confidence bands, okay? So the confidence bands are going to be generated using our impulse response function, which is just a line. And then to this line, we're going to be adding the standard deviation. So the standard practice is to include 2 standard deviations. And here I'm going to generate now the low confidence band. The way you generate the low confidence band is just by subtracting the 2 standard deviations. Perfect. So this is basically everything we need. We're going to run this and we're going to see what we get. Okay, so the first thing right away I get is an error, and the error I'm getting is basically I type incorrectly the name of my file. So the name of my file is IRFs with an S at the end. So make sure that you don't have any typos. Let's go again and see if we get the correct output. Perfect. So there we go. It's great that I actually got an error, because then you guys can see live how you can basically go through the errors and make sure how you can fix them. Okay, so here we have the output. We have generated here a new series that contains the confidence band, the superior confidence band, and the lower confidence band. In step number 5, we're going to plot each response variable. For this particular case, I have already included the whole code here because it's going to take me a long time to type it live. The command we're using is two-way. We're plotting 2 things. We're plotting the area of the confidence bands, that's you can see here, high and low, which are the 2 variables we just generated. And we want to do this for the variable of non-farm payroll employment. This is EM. You're going to repeat this process for all the variables, okay? For PCOM, you're going to be using it for all of them. Then the color I have used is that gray color, that's the GS14. Then we have a line for the impulse response where I'm using a black line with medium thickness. Then I'm using a white line. I'm using a title to include a title, X title, Y title, and then I'm putting white color as the background. Then I'm giving a name. Very important, you have to name this plot. I have named it G_EM, but you can name it whatever you would like. So let's go and let's run this file. And here in the screen, we get now the graph that is the response of EM, which is the non-farm payroll employment. You're going to generate this for all the variables. Remember, all of them, you have to plot them, and then we are going to combine them all together. The last thing we're going to do is to combine the graphs. I'm using the command graph combine, and you're going to type here all the different graphs. Remember, I've shown you how to produce the first one that I have named it G_EM. We're going to produce them for all the rest of the variables, and we're going to put them together. We're going to execute this do, and we're going to see how the graph looks like. And here we go. You can see that we get a professional graph and looks exactly as that one that Evans and Marshall 1998 produced. I would like to invite you to subscribe to my channel. Please give it a like. Please leave your comments. I want to know your thoughts. I want to hear your feedback. I want to hear what you would like to see in coming tutorials. But for now, this is going to be everything. I'm going to see you in video number 3, where I'm going to show you how we can extract the structural shock, which we are going to include it in the local projection method.